This is Cosmographia, the Randall Carlson podcast. Welcome back, ladies and gentlemen. This is Cosmographia, the Randall Carlson podcast. And we are trying to get back into the swing of things. Randall's been busy. Randall, you've been going around giving presentations in a few different places. And we've got trips that we've been going on and trips that are coming up. But yeah, we are trying to get back into doing at least one podcast or live stream a week. So here we are. This is episode 99. Is that right?
99,
guys.
Cool.
Wow.
99.
We have plans for 100. We're going to get dressed up.
We better make plans.
Yeah.
I don't think we should just let 100 come and go with no particular notice or nothing special.
Do you live in a cave now?
I know I've thrown out toga multiple times.
Toga, yeah.
Beyond that, we're going to have to define a little
I'll
clarity.
make a special graphic to use as my backdrop.
There you go. Put a UFO back there. That'll be your special graphic. Yeah, with Snake Bros, we just waited till 200. We went right past 100 without doing anything.
You just breezed right by it.
Yeah, and then we got to 200. We're like, maybe we should do something. So, but yeah, we ought to do something. But this is great. I can't believe we're at 99 already. So it's fantastic.
We're coming up on 4 years, so we're gonna have to pick up the pace.
Yeah.
Yeah.
Yep.
Well, it's true. We've been neglectful, but it's all because I think most of us have been traveling a lot.
Yeah. Brad just got home, right? Brad?
Yeah, Brad especially.
Extended trip.
Yeah, I had a long road trip. Just got home middle of the night 2 nights ago. So yeah, I'm still unwinding a bit, but totally
Brad
worthwhile and setting up some new ideas for tours.
Yep.
Yeah, it looks like he's in a cave. Yeah.
Well, this is kind of what the rocks look like out in Utah and Arizona, where I've been tooling around. Last place I stopped was Colorado National Monument on the way through Grand Junction and then 70 cross country. So, yeah, this is what the rocks look like. A lot of places out there.
So you did a recon for a potential Bonneville flood trip.
Definitely would like to try to pull that off in 2024. There's as usual, more places than we're going to get to in a 5 or 6 day tour. But somewhere I think we'd start off in Salt Lake City and check out the side of Lake Bonneville itself, go across the Snake River Plain, and then end up in Boise.
Mm-hmm. So you went up through Red Rock Pass, I assume, when you made your recon. You were in Salt Lake City?
Definitely went out to Antelope Island, went up through Red Rock Pass, went up through Pocatello and the narrow zigzag stretch where the floodwaters rushed through before they made the big fan out there in Pocatello and American Falls.
Mm-hmm.
And then, the Mallard Gorge and, just many sites. It's a beautiful, unique area. And the interstate actually goes down into the canyon for a couple miles. So it's really just an impressive drive across Interstate 84.
So you did the falls. You go to the Perrine Bridge.
Did go to the Perrine Bridge. Yep, definitely. They got a big new walkway and visitor center there. So both sides of the bridge, lots of overlooks there. And they're actually doing base jumping. A guy approached us to see if we wanted to do base jumping with him.
We're going to put that on the tour? We should put that on the tour. We should put that on the tour, base jumping.
Yeah.
If that's the only way to see the canyon, is to jump off the top of it, fall down into it.
Yeah, it's pretty expensive. But when we drove by a couple days later, we saw somebody actually up on the rail and jump off right as we were driving by on the bridge.
Yes.
Yeah, that sounds fun.
That's
pretty crazy.
Wow.
That's about 450 feet deep there, I think, at Twin Falls. But I went to Shoshone Falls, and it was more volume than we've ever seen because, again, I've gone in the spring, right? We've always gone in the late summer, and everything's dry. Just a trickle out there. But, it was gushing, so that was beautiful.
I got to see that.
Places that we would hit on a tour.
Yeah, all right. But you didn't do the Bruno Dunes, right?
Did get out to the Bruno
you did.
Dunes.
That's
didn't
right.
Didn't get to Bruno Canyon.
Okay.
It's super windy out there a lot of the time, and that's their reasoning for how that 400-foot high plus tallest dunes in the country or the continent even have collected in that semicircular basin there.
Mm-hmm.
But they're actually renting little sandboards that you can, like board down the dunes on. So we saw some people doing that. So watch that. But yeah, it's like you're getting
that
sandblasted
sounds like a
out
lot
there.
that sounds like a lot of fun.
Yep. So
we're both snowboarders.
They've got
so
an
we
observatory and a new observatory out there. So yeah, we started talking to the woman at the visitor center about setting up a program where we could come, during the day and then stay at night and get a professionally run observatory view of the sky.
That'd be great. That'd be a nice little bonus to include in a tour. Absolutely. And then you guys got up to the bottom end of Hell's Canyon. Is that what you told me? You got
yeah, we went to the end of the road. As far as you can go, you get to the Hell's Canyon Dam, and you can get a little beyond it, and then that's where the put-in is for the jet boat tours.
Mm-hmm.
And again, that was just rushing, gushing like crazy. It was just so much volume coming out. They're releasing through the dam.
Oh, I bet.
Yeah, so they're just starting into the season where they'll take people several hours downriver into the canyon beyond where you can drive, and then you jet boat back up, however many miles it is. I didn't get the details on that, but yeah, it's a early morning excursion and spend a lot of the day doing that. So that would be probably a bonus, like 2-day add-on to the trip, because it's over 3.5 hours just to drive down in there.
Yeah.
One way, and then you have to come back out the other way. So
then they do have boat tours, though, to take you through the whole canyon, like takes multiple days up to like Lewiston or Clarkston. Do they go do that?
I don't think they go that far.
Okay.
But there's lots of rafting trips and water companies. We went through a town called Riggins on the Idaho side that's pretty much parallel to the canyon, and there's a bunch of whitewater rafting. The Salmon River goes through there, and there's access into Hell's Canyon, so they do multi-night rafting trips, etc. But I don't know about all the way to Lewiston.
Okay. Well, that'd be quite a tour, wouldn't it?
It's freaking gorgeous. It's unbelievable. When you and I went up there, right, we didn't know what we were getting into, and it was dark by the time we even got down to the dam, so we couldn't see anything. So we went up in the morning time, so got to see it, and again, just green and beautiful and really dramatic being a mile down. Yeah,
so should mention for those that don't know, Hell's Canyon is the deepest canyon in North America. Deeper than the Grand Canyon. I don't know how much deeper, but it is deeper.
Not much, but a whole lot narrower.
A whole lot narrower.
Narrow.
Yes. Now, what, of course, is the thing I'm curious about is how much deepening was caused by the Bonneville flood. If the Bonneville flood could have removed hundreds of feet of basalt bedrock across the southern plain, it probably had to have removed at least that much. Over deepening the canyon. I haven't looked, but I bet you the gradient steepens once you get to that. Well, it would make sense that where the dam is, would be a logical place for the gradient to steepen, as compared to the average gradient east to west across the southern Idaho plain, which I'm guessing is pretty level, along there for the most part, which would imply to me that it might even be that there'd be more erosion and more deepening of that canyon because those waters, that 300-foot drop, 300-plus foot drop, the estimates I've seen is that took about a year to accomplish. So it means that you had 40 million cubic feet per second running through that canyon for about a year. So
which 300-foot drop at Red Rock Pass?
Well, I'm guessing the bottom of the canyon now compared to the top of the cliff. The canyon's about 400 feet deep, And I said 300 because I'm going to assume that there was already a canyon there.
Which, I'm sorry, we were in Hell's Canyon, which is a mile deep. So where are we at 400 feet deep?
Well, back in Snake River Plain, by Bryan Bridge there.
In Twin Falls, yeah.
Yeah, because what I'm trying to do is extrapolate from how much we could estimate that canyon got deepened.
Okay.
And we could probably conservatively apply that to Hell's Canyon, because what I'm saying is I think at Hell's Canyon, the gradient actually gets steeper.
Probably. But you're in that really disturbed area, right? That used to be the Yellowstone hotspot, and where the basalts that filled up the Columbia Basalt Plateau up to 10,000 feet or even more in some places, right? Flowed out of there. So, it's really disturbed and craggy to start with. Yep.
Obviously a very interesting landscape. And then the feeder dikes are all in there that I haven't seen. You may have seen some there, but not recognized them. But there are the feeder dikes where the basalt lavas, where the magma was coming,
I would like to have been able to identify that, but I don't know that I saw that specifically.
Right. Well, they've been identified. A lot of
territory there that you can't really access.
Yep. So anyway, with that great trip, good recon, Brad. And then you went up.
Fantastic. So I'd love to get people out there and show them it next year and hopefully every year.
Well, the difference, I guess, between that and the Scabland tours we do is that there we would it wouldn't work to have a central location.
Correct. We got to be mobile.
Got to be mobile. But anyhow, that would be a great trip to do. That'd be a great complimentary trip to the Missoula flood trips. So we're on 99. So 98, we were kind of leaving it off. I know we were talking about the carbon fertilization effect and the greening. Some of the initial studies about the greening of the earth, and there's some interesting new stuff that's come out recently, and some stuff not quite so recently that we haven't really talked about, but that I think definitely has bearing on our conclusions about, whether or not this increase in carbon dioxide is the disastrous affair that it's being made out to, or if there's another side to the story of increased carbon dioxide. So that was kind of one of the things we were addressing in several of the previous podcasts that we were doing. And I think we were starting to look at some of the stuff that, some of the crop studies. We were looking at some of the enhancement of the growth of the yields that were due to carbon fertilization. Isn't that where we kind of left off?
Sounds about right.
Yeah, and we were kind of, getting into some of we got a lot of stuff on the sun that we got to talk about. So I'm going to have we'll do a whole presentation or several on dealing with the role of the sun in all of this. But a few things, I don't know. Now stop me if we've covered this specific material. But this is going back here. We'll go back to 1997. This is Graham D. Farquhar. This appeared in the journal Science, which is considered, peer-reviewed, prestigious journal. It's been around for many, many decades, even going back to the 1800s. So this was when it was first dawning on scientists that perhaps anthropogenic enhancement of carbon dioxide could be could be enhancing biomass accumulation, could be enhancing, leading to greater tree growth and forest growth and things like that. So this guy, 1997, was probably one of the important papers that shows kind of this shifting in the thinking and the acknowledgement that this carbon dioxide fertilization is underway. So he says what happens to vegetation when greenhouse gases, mainly carbon dioxide, increase in concentration and the temperature goes up. the Framework Convention on Climate Change. Now, this is the Framework Convention on Climate Change is the group, the UN working group that established the Intergovernmental Panel on Climate Change for the purposes of providing a scientific rationale for the policies that were being developed in the Framework Convention, right? So it started with the Framework Convention. That was the UN. It was not considered to be a scientific group. It was a political group made up of representatives and dignitaries and bureaucrats and stuff from the different nations. So this was the Framework Convention on Climate Change. So they established the IPCC to be the wing of working scientists that would provide the rationale for the policies that were being contrived in the Framework Convention. So he says here, the Framework Convention on Climate Change commits the signatories to avoiding dangerous interference with the climate change. Laudable goal, of course. Interference that might harm the world's agriculture and natural ecosystems. But just what are the likely responses of vegetation? So then he refers to Street Parrott, who was studied the paleo-environmental history of high-altitude lakes in Africa. So her and her colleagues, after studying these high-altitude lakes, examined the lake sediments, the pollen and leaf waxes that were in them, and the carbon isotope composition of the bulk organic matter and of other specific biomarkers. Their conclusion, this was their conclusion, that the increasing concentration of carbon dioxide in the atmosphere since the last glacial period has allowed trees to grow where the vegetation was before 13,000 years ago, restricted to an almost treeless grassy heathland. So, Ice Age, prior to 13,000 years ago, a treeless grassy heathland. And now there are trees, forests growing there. And Street Parrott and her colleagues attributed this presumably to the increase in temperature, obviously, but the increase in concentration of carbon in the atmosphere since the last glacial period has allowed trees to grow where the vegetation was before 13,000 years ago, restricted to a treeless grassy heathland. Acknowledging that carbon dioxide concentration itself affects the growth of trees enables us to see that the cooling of tropical land was not so great as we thought. Along these same lines, Sage has argued that agriculture, and I can get these references if anybody wants them, the references that they're making here. Along these same lines, Sage has argued that agriculture became viable at several places around the world between 11,000 and 6,000 years ago, only when the CO2 concentration became sufficiently large to sustain decent yields for our first farmers. That's an interesting. So not only the role of the increasing temperature, but the increasing carbon dioxide from 180 to 280 parts per million. So, in other words, the implication here of this is that when you're at that glacial low of 180 parts per million, is there even enough carbon dioxide to sustain high-yield crops of any kind? For the individual plant, water use efficiency is almost directly proportional to the level of carbon dioxide for a given regime of temperature and humidity.
Can I ask a question real quick?
Please.
How far back do you have to go before the Ice Age period to get back to, CO2 levels that we have today or that we've had recently?
Oh, probably. Well, it's hard to tell. Regionally, There's probably been places, because we haven't talked about the record of stomata, plant stomata, which shows carbon dioxide concentrations all over the place, up to even, 4, 5, even 600 parts per million pre-industrial times or even early industrial times. The question is, are we talking about global or is this a regional Because our assumptions now is we have our carbon dioxide monitoring stations are in Hawaii. So you're grabbing carbon dioxide, you're grabbing samples of the air, looking at how much carbon dioxide is in it over Hawaii, right? So now the assumption is that that's pretty much uniformly distributed around the planet. But is it? Well, the stomata results would suggest that maybe it isn't. That maybe there are places, particularly over land, where you're going to see much higher concentrations.
Okay.
And we can get into that some.
It's just interesting because you're mentioning how it affects crop growth, and I'm just thinking also that it's not too soon, not too long after the end of the Younger Dryas that agriculture just begins.
Yeah.
And
yes.
It's like almost as soon as they had enough CO2 in the atmosphere, they start having organized growing of crops. It's interesting.
It is. So, and this is interesting too. Okay, I when I first learned about this, I just thought this was extremely fascinating and important. For the individual plant, water use efficiency is almost directly proportional to the level of CO2 for a given regime of temperature and humidity. So, concentrations of 180 parts per million, such as occurred during the late glacial maximum, being half the current levels, would mean that plants had to transpire twice as much water then as now to achieve the same level of photosynthesis. Put another way, doubling the CO2 concentration is like doubling the rainfall as far as plant water availability is concerned. Further, increased greenhouse forcing also speeds up the global hydrological cycle. And so, on average, the actual rainfall increases with increasing CO2 concentration. So now you've got doubling the efficiency, the water use efficiency, with the increase in CO2, and you have actually enhanced rainfall as a result with the CO2 concentration.
I'd be curious how that works, too. I mean, is it like increasing CO2? Why does that increase the rainfall?
Well, I think it's more having to do with the temperature.
So it's just correlated.
Correlated, yes, not causative.
Not the cause, okay.
Right. But that would be, it would certainly be correlated in the sense that the warming temperature. But the way he says it here, increased greenhouse forcing also speeds up the global hydrological cycle.
Okay, greenhouse forcing. Okay.
Greenhouse, yeah.
So, yeah, I would interpret
that's the causal connection, is the greenhouse effect.
And so, on average, the actual rainfall increases with increasing CO2 concentration. So, both photosynthesis and the enhanced greenhouse effect are more sensitive to CO2 levels when the concentrations are low. We've talked about that, right? The greenhouse effect is much more effective at, say, 100 parts per million. Like that, from 0 to 100 parts per million, there's way more capture of heat than there is from 300 to 400 parts per million.
Yeah, the greenhouse effect of CO2 specifically is more effective at lower levels.
Yes. So the translation of increased photosynthesis to increased growth rate is not straightforward, depending on developmental processes. The effect of the 180 parts per million increase from the late glacial maximum to the present should be much greater than the effects of going from 360 to 540 parts per million. And this is referring again back to we've talked about as the logarithmic effect, the thermal capture effect. We've looked at the graphs, how you've got that logarithmic, comes up sharp, that first 100 parts per million, and then starts tapering off. And once you get to 3 to 400, it's insignificant.
Yeah.
Right. And we talked about how the computer model have to introduce a series of,
feedback loops and
feedback,
stuff like that.
Positive feedbacks.
Yeah.
that self-amplifying positive feedback.
Right.
So the effects of the 180 part per million increase from the late glacial maximum to the present 360 parts per million, so this is back in 97, should be much greater than the effects of going from 360 to 540. The latter being twice the pre-industrial level. In other words, pre-industrial level 280 parts per million. Double that, you got 540. The plants of today are much less water and CO2 limited than they were at the late glacial maximum. Nevertheless, one suspects that the direction of change in the near future will be the same as that following the late glacial maximum, one of increased effective rainfall with the agricultural and ecological consequences that follow. Given that the availability of water, now this is important, given that the availability of water for agriculture is already becoming such a problem, this aspect, at least, of atmospheric change is a welcome one. So, yeah, I think we talked about the, actually, because this is jumping back to 1992. Tell me if we already covered this, but maybe we didn't. This was also in Science. It's three authors here. Pekka E. Kauppa. The title of the article is Biomass and the Carbon Budget of European Forests, 1971 to 1990. The facts about forest resources seemingly contradict. Now they say, yeah, this is when they really begin to accumulate a whole series of satellite surveys of actual forest growth. So previously they had been making projections, and those projections were based upon essentially the assumption that forest land was going to continue to be lost for whatever reason, primarily, I guess, through agricultural, through industrialization, all of that, right? So it says here the facts about forest resources seemingly contradict the widely held view that European forests are declining. So the facts about those forest resources contradict the widely held view that was still widely held in 1992. We first elaborate on reasons for the increase of forest resources, and then describe pitfalls in the interpretation of forest health surveys, which have contributed to pessimistic views about European forests. Lawson reports that growing stock and timber growth potential in the United States have been repeatedly and seriously underestimated because they're not taking account of the carbon fertilization effect. An increase of forest resources can be explained by factors such as silvicultural development, favorable climatic conditions, without specifying what would be the favorable climatic conditions. Well, the 20th century increase in temperature. That's basically what would be implied by that statement. And then finally, the fertilization effect of additional carbon dioxide in the air and the deposition of plant nutrients.
So is what's happening is people are making projections based on all these ideas about the forest being destroyed for usage.
Yes.
But they're not taking into account that actually it's growing better because of more CO2. So then when somebody goes out there and actually counts, or they use satellite images to count it, they're like, wow, it's much better than they were projecting. Is that?
Yes.
Okay.
That's what he's saying. That's the gist of what I just read.
Okay.
Yeah. So then we get back to Sherwood B. Idso, who we introduced, and his son is carrying on his work that we introduced in the last discussion. This was from the Bulletin of the American Meteorological Society. It came out in 1991. And this is what Sherwood is saying. He says the question of ultimate surface temperature increase thus comes down to one of estimating the maximum amount of CO2 that man is likely to release to the atmosphere in the years ahead. A doubling of current emissions, for example, would lead to an atmospheric CO2 content on the order of 700 parts per million, which would probably be climatically acceptable, but only if Earth's forests are not decimated in the meantime. On the other hand, if the forested area of the globe could be increased, even greater quantities of CO2 could safely be released to the atmosphere. In this regard, nature becomes our ally. And we did get into this, but it's worth. As increases in atmospheric CO2 result in growth rate increases of trees 5 times greater than growth rate increases in non-woody plants. Hence, as the CO2 content of the air continues to rise in the years ahead, woody species will begin to expand their ranges, as is already happening in many parts of the world. My R.B. Maineni and others, I don't know how many others, this was in Nature, the British Journal of Science, in 1997. We see that in the 90s, they're really becoming aware of this effect of, the greening, if you will. This is called increased plant growth in the northern high latitudes from 1981 to 1991. Variations in the amplitude and timing of the seasonal cycle of atmospheric CO2 have shown that an association with surface air temperature consistent with the hypothesis that warmer temperatures have promoted increases in plant growth during summer and or plant respiration during winter in the high latitudes. Here, we present evidence from satellite data that the photosynthetic activity of terrestrial vegetation increased from 1981 to 1991. The winter and spring warming of the interior of the continents of Asia and North America in the 1980s may be a result of natural causes not yet explained, but its timing is consistent with an enhanced greenhouse effect caused by buildup of infrared absorbing gases in the atmosphere. Although it amounted to a departure of only a few tenths of a degree from previous record temperatures, it was associated with far greater warming in the spring months at high northern latitudes. Biospheric activity there, based on our analysis, increased remarkably as a result of this warming.
So the tiny bit of warming had a massive effect in the spring. Is that's
Yes.
Okay.
Yes. And the activity and increased productivity and increased biomass.
Okay.
So let's see. And then, so this shows the same thing. Balancing the carbon budget from 2007. Experiments have shown that most C3 plants, which is all trees, many crops, and vegetation from cold regions, respond to elevated concentrations of CO2 with increased rates of photosynthesis, increased productivity, and increased biomass. The biomass response to elevated CO2 averages between 20% and 30%, based on measurements from more than 100 experiments. The pools of carbon in the litter and soil carbon also increase under elevated CO2. Warmer temperatures and changes in soil moisture often favor the growth of trees, and in the longer term, the spread of trees into tundra, savannas, and grasslands. Increased temperatures in cold ecosystems, for example, tundra and taiga, increase productivity and carbon storage. One aspect of warmer temperatures is longer growing season, as observed over the boreal zone and temperate Europe. The factors described above often interact non-additively to influence carbon storage. For example, high concentrations of CO2 enable plants to acquire the same amount of carbon with a smaller loss of water through their stomata. This increased water use efficiency reduces the effects of drought. Higher levels of CO2 may also alleviate other stresses in plants, such as high temperatures and ozone. The observation that productivity is increased relatively more in low productivity years suggests that the indirect effects of CO2 in ameliorating stress may be more important than the direct effects of CO2 on photosynthesis. In other words, increase the amount of CO2 in the atmosphere and plants respond by being healthier and more resistant to stress. CO2 and nutrients may also interact synergistically to increase carbon storage. Nitrogen fertilizer and elevated CO2 together had a greater effect on forest growth than the sum of their individual effects. The relative stimulation was again greater in a nutritionally poor site. So in other words, think of it this way. The parts of the biosphere, the ecosystems that are under stress are not healthy. They respond even stronger than the rest of the biosphere with the increased carbon dioxide concentrations. Of course, none of this stuff is actually, you don't hear any of it, through mainstream media. They never talk about these studies. Then 2008, tree and forest functioning in an enriched CO2 atmosphere appeared in the New Phytologist. Henrik Saxe, David Ellsworth, James Heath. Forests exchange large amounts of CO2 with the atmosphere and can influence and be influenced by atmospheric CO2. There has been a recent proliferation of literature on the effects of atmospheric CO2 on forest trees. More than 300 studies of trees on 5 different continents have been published in the last 5 years. These include an increasing number of field studies with a long-term focus and involving CO2 by stress or environmental interactions. The recent data on long-term effects of elevated atmospheric CO2 on trees indicate a potential for a persistent enhancement of tree growth. Recent studies indicate that elevated CO2 causes a more persistent stimulation of biomass increment and photosynthesis than previously expected. So there we go. Study after study is showing the effects of increasing carbon dioxide. Now, that's not to say that all of the effects are good, but interestingly, in the public discussions that we're seeing about climate change and the climate crisis, that side is completely ignored in favor of the idea that the increased carbon dioxide is going to cause some kind of climate disaster. Which, I think is fair to ask, is that based upon sound, reasonable science? Is that based on the actual facts and the evidence? That side of the equation. Now, I've shown you just a little bit here that it in effect shows, well, yeah, there absolutely is positive effects of a mildly increased temperature and the increase in carbon dioxide concentrations. This has been well established. That's what I just, the quote I just read you, that there have been, more than 300 studies of trees on 5 different continents. This is actual data that supports the notion that there is a positive side to this increase in carbon dioxide. Now go to the other side and look at the evidence that there's going to be a carbon dioxide-induced climate disaster. How strong is that evidence? Well, I've tried to show, and I have shown, if you've watched the last 10 or 12 or whatever episodes, how the data is manipulated and how it's presented to the public. We looked at tornadoes, we looked at hurricanes, we looked at summit droughts, we've talked about wildfires. None of these have we really taken a deep dive into looking at the comprehensive mass of evidence around these things, but enough to show that in all of these areas, it is highly questionable. In a minute here, I'm going to pull up the latest accumulated cyclonic energy graph so we can look at that. I think it's up through hurricane season of 2022. We've looked at this graph before. It's a great graph. It's republished every year. we can go here.
Should we take a break before we pull that up?
Sure.
Close to it.
Yeah, let's take a little break. And I will be prepared to.
All right. Well, we'll be right back, folks.
Well, Mike, before we, launch back into it, would you like to, take a few minutes and kind of share some of your feelings and thoughts about your new celebrity status to all the fans out there?
I have no idea what to say. I was startled when I encountered it for the first time. I don't know.
People are jealous, Mike. Other people are jealous that people saw you and got to talk to you.
Yeah.
The elusive, quiet Mike, the normal guy, was spotted in the wild.
He has been seen in the wild. In his natural environment.
Yeah, lugging pounds of video equipment, cases of video equipment, and looking startled, like, what?
Yep. A normal guy in the headlights. And we're back, ladies and gentlemen. Kosmographia.
Okay.
Back from the break. Are we going to continue on, or?
Well, yeah.
Okay.
Or we could all just sit here.
That's what I do.
I like.
Well, yeah.
I'm going to try to, feel it out when Randall thinks the show has already started, and just let's roll with it. Yeah. That was a good intro.
Yeah, I'm sorry about all that discussion we were having about the pyramids and the mounds. I was thinking that was all. I don't know how I could have thought that, because we didn't obviously have the big dramatic roll in, but anyhow, but I like Brad's idea. That could be some good little bonus stuff.
Yeah.
Put that out there. Yeah. Okay. Well, anytime.
We're going.
Oh, we're in.
Yeah, we're in.
We're in,
bro.
Oh my. Okay, so now we actually are in. Okay. I was waiting. Where's the big dramatic? Well, we're back, folks.
Welcome back from the break. Usually,
Well, he said that.
Yeah,
he did. Where was I?
Yeah, I liked the introduction with Mike, so I was just like, yeah, let's do it.
Yeah.
Oh, okay. So did that all get recorded? I didn't even think that when I said that.
Yeah, it's recorded. So
it's running the whole time.
Kyle's introduction back into the show, you just back it up a little bit, and we can include Mike's sighting in the wild.
All those faces you made.
Yeah.
No.
If I ever get to one of your adventures out west, well, I'll just have to learn to adapt, I guess.
Yeah.
I know. Listen, I know
famous,
there's a
Mike.
wild guy inside there just waiting for an opportunity to get out.
That's right.
Bring your guitar, Mike, and we'll put on a show.
It'll be
All
like
right.
every night Mike's partying until 4 a.m.
Yeah, yeah.
Having
Yeah.
to drag him out of his room.
Well, we got a project going with Mike right now. We're building a pergola for Mike, so I got to get over there tomorrow and see what they're doing.
Huh.
Yeah. What are you going to do with that pergola? You're going to let
Is that where you go when you're like you don't get to go to heaven? You're not going to hell?
Yeah, you go to the
No,
pergola.
pergola is not purgatory, but
They're related, perhaps.
So it's basically a prison.
Well, no, think
Randall's
about it.
team
It probably
building.
is related, because a pergola is sort of an intermediary between the inside and the outside.
yeah,
Aha.
And
Okay, so the words
purgatory
are
is an
related, yeah.
intermediary between heaven and hell.
yeah, okay.
So there we go.
Now I had to take a pecan tree down that was shading the back end of the house, or the
Oh,
west side of the house. So now it's getting full sun.
uh-huh.
So I need a pergola to create some shade back here.
Well, it's going to be nice. It'll be a work of art. You know that.
It is, yes.
And are you going to let biomass accumulate on it?
I don't know. Maybe planting some jasmine vines or something.
Okay.
Grape arbor. Who knows?
Yeah. Well, I'm going to have to get over there and see what they're doing. I know they were scrolling the ends of the joist there today. on yesterday. Yeah, I think it's going to look nice.
It is.
Mm-hmm. Okay, so we were talking about carbon dioxide.
We're getting into the cyclonic.
The cyclonic
Graph.
Yeah, that's a cool graph. So let me see if I can pull that up here. So yeah, there's just been a new one updating of the accumulated cyclonic energy that just came out. Yeah, here we go. So what I'm going to do is I'm going to go back. We'll revisit some of the ones that we've already looked at, just so you can see the trend here. Share screen. You are sharing. Okay. Total accumulated cyclone energy. So that's your ACE. ACE. 24-month running sums. So in this particular graph, you can see we're starting in 79 and coming up to 2009. And energy's on the left. This is your global, and this is your northern hemisphere hurricanes. Global hurricanes, northern hemisphere hurricanes. And you can see year by year, you can see that they were fairly low in the 80s, and then there was a big spike in the 90s. Then it went down in the early 2000s. Then there was another spike in about 2005, 2006. Then we come here for up to 2016. Compare. Here you see this double spike, followed by this. It's trending down. And then you can see what it's done. It's trended down. And then as we get into 2015, 2016, you see it spiking again. Do you see the last 4 decades of global and northern hemisphere accumulated cyclone energy? 24-month running sums. Note that the year indicated represents the value of ACE through the previous 24 months for the northern hemisphere, which is the bottom line in the gray boxes, and the entire globe, which is the top line in the blue boxes. The area in between represents the southern hemisphere total accumulated cyclonic energy. So in effect, when you've got a lot, this means you got a lot of hurricanes or typhoons. And here you have low numbers of hurricanes and typhoons. So here's your, over here it says your accumulated cyclone energy in knots. So this is the wind speed, and a knot is, let's see.
Yeah, I was wondering, what are they measuring? Like average wind speeds of the cyclones, or?
Yeah, this is, so this is the accumulated cyclone energy in 10,000 knots squared. So that's the accumulated cyclone energy. So that's 10,000 knots squared. 10,000 knots squared. I'm going to play with that. I'm going to go back to, I did read Maui's original explanation for this, but it's been literally 10 years ago. It's more the graphic depiction, though, that conveys.
Yeah.
So then the next one gets us up to 2022. So here we go. This one I like a little bit. This is, so all hurricanes greater than 64 knots. So 64 knots is 73.65 miles per hour. And then your major hurricane, so he's broken the graph up a little differently here.
Okay, right here it says they do this, they calculate by summing the square of a tropical cyclone's maximum sustained winds measured every 6 hours.
Okay, summing the square of the tropical, there we go. Okay.
And then the resulting total is divided by 10,000 to make it more manageable. So
right.
Okay.
All right. But here it's a little easier to interpret because it's directly the number of knots. So all hurricanes greater than 64 knots, and 64 knots is 73 miles per hour. Major hurricanes at greater than 96 knots, that's 110 miles per hour. So this is all hurricanes on top, and this is major hurricanes per year. So here's your major hurricanes, and there's less of them, obviously, at 96 knots, which I can see here is 110 miles per hour. And then all hurricanes, obviously there's going to be more. Thing to keep in mind, though, of course, though, is that just like with tornadoes, there's more hurricanes being reported than there was before. And we've increased the number of named storms. So,
but it looks like there's an overall downward trend from 90 to like 14. There's this long downward trend, and then it kind of jumps up after 14.
But it doesn't jump back
it
up
just
to
two spikes,
it's
really.
Still less than the 90s.
Yeah.
And even into the 80s. So, I mean, what you're seeing here is that over a 40-year span of time, there's certainly no upward trend discernible.
No.
This was an ENSO year here, El Nino Southern Oscillation.
Yeah, I see that's that's the highest major hurricane spike in the whole graph right there in 2016.
Yeah, it is. So what this is showing us here is that, and this is accumulated, this is Atlantic hurricanes and Pacific typhoons, both Northern Hemisphere and Southern. So it's for the globe. It doesn't count specific hurricanes as much as it does looking at the total energy expended. And of course, the total energy expended is going to be directly related to the actual numbers of events, typhoons and hurricanes. But this next series of slides, which we haven't looked at before ever, is quite interesting. These are the deep blue holes that are in the Western Atlantic, and they serve as repositories for sediment. And during extreme weather events, mainly hurricanes, lots of more coarse sediment is flushed into these holes. So what this study did was it extracted cores from the bottom of these deep holes in the ocean floor where these layers of sediment is accumulated. So this is a report written by one of the lead scientists. It's written for probably an online journal called The Conversation, and this is what it says here. This is Tyler Winkler. He's a postdoctoral researcher in oceanography with Woods Hole Oceanographic Institution. If you look back at the history of Atlantic hurricanes since the late 1800s, it might seem hurricane frequency is on the rise. The year 2020 had the most tropical cyclones in the Atlantic with 31, and 2021 had the third highest after 2005. The past decade saw 5 of the 6 most destructive Atlantic hurricanes in modern history. Of course, now when you're talking destructive Atlantic hurricanes, the yardstick for that is the destruction of infrastructure, right?
Yeah.
What is the dollar value of what was destroyed? So, of course, if you look at the extreme amount or increase of coastal development that has taken place in the last few decades, of course, anything that makes landfall, if it makes landfall on the west coast of Florida, say last year as compared to 50 years ago, obviously, even without any adjustments for, even with adjustments for inflation, there's going to be a huge discrepancy in the amount of actual damage to buildings and roads and power lines and all the rest of that stuff, right? Because there's so much more of that now, right? Okay, then a year like 2022 comes along with no major hurricane landfalls until Fiona and Ian struck in late September. The Atlantic hurricane season, which ended on November 30th, had 8 hurricanes and 14 named storms. It's a reminder that small sample sizes can be misleading when assessing trends in hurricane behavior. There is so much natural variability in hurricane behavior year to year and even decade to decade that we need to look much further back in time for the real trends to come clear. Fortunately, hurricanes leave behind telltale evidence that goes back millennia. 2,000 years of this evidence indicates that the Atlantic has experienced even stormier periods in the past than we've seen in recent years. That's not good news. It tells coastal oceanographers like me that we may be significantly underestimating the threat hurricanes pose to Caribbean islands and the North American coast in the future, which is certainly, I think, a legitimate cause for concern, because what it's saying is that if we look in the past, we see that there have been episodes that have been more stormy than modern times. Well, what we have to do now, breaking this down, is we have to acknowledge that these stormier episodes in the past had to, by implication, be natural. And then we contrast that with the assumption that hurricanes are supposedly increasing in ferocity and intensity and so on in recent years because of global warming. But what we see, in fact, is essentially the opposite of that. So let's go to the next one here. So this is showing here on the right, you'll see a sample of the core. And you'll see this, you've got this coarse layer that's sandwiched between finer grained sediment on top and bottom. This coarse material represents a hurricane. And so by taking these cores and analyzing these coarse sediments, not only the how coarse they are, but the stuff that's in them, which will tell you something about, obviously a wind moving at 200 miles an hour or 150 miles an hour is going to be carrying material from far distant places much more effectively than a 20 or 30 mile an hour wind, obviously. And then over here, if you look at here, this is your greater than 250 micrometer sediment in milligrams per cubic centimeter. So this is your depth, your sediment depth over here. So you're going down in centimeters, right? So you're going down here, and what you're seeing over here with these yellow boxes is rough dates, right? So the deeper you go, the farther back you're going, right? So you can see here at the top, 1980, and then we're getting down 470 plus or minus 15, 415, 490, 500. So they're generally dating a little bit older. But of course, again, there's going to be discrepancies because it's not going to be uniformly linear, because different hurricanes are going to be bringing stuff in and depositing in those holes that might be older or younger. Over the longer term, yes, there'll definitely be a trend. So they're going back down here to the bottom 1,000 years ago, right? So what you see here is is that the numbers of hurricanes have declined considerably in the post Little Ice Age warmth compared to these early. So, I mean, here's the last 100 years or so, right? And here's the last 900 years. So this clearly does not show, at least in the Western Atlantic, does not show an increasing trend in violent hurricanes. In fact, it's showing just the opposite. Now, does this apply to the whole? No, this is pretty much
at least not ones that happen to occur where they could drop sediment in that particular hole.
Correct.
Right.
Correct.
Yeah.
So, I mean, but there was this study involved, I think, about 6 or 8 of these holes. So it wasn't just one hole. It was not one hole. I think there was like 6 or 8 of these holes that were. So it's pretty much Western Atlantic in the area of the Bahamas, which of course is dead center of the paths of most hurricanes. So if we go to the next slide here, the compiled Bahamian records document substantially higher hurricane frequency and this is quoting this guy, the Northern Caribbean during the Little Ice Age around 1300 to 1850 than in the past 100 years. That was a time when North Atlantic surface ocean temperatures were generally cooler than they are today. But it also coincided with an intensified West African monsoon. The monsoon could have produced more thunderstorms off the western coast of Africa, which act as low-pressure seeds for hurricanes. But if you look at the top up here, I think I've got the next one is a bigger. There we go. So, yeah, if you look here, so this is hurricane per century. Let's see. Hurricanes per century, you can see going up and down, and then you get to the medieval warm period. They dip down, then they come up, and then you see right here is in this particular blue hole that we were just looking at, you see that there's a big spike. Look over here, hurricanes per century. Yeah, per century. And this is in the years. So you see up here 1,600 years. So this is the depth of the Little Ice Age right here. And you can go down, you'll see the same thing happening here. And then there's a decline in frequency as we come up between 1,800 and 2,000. And then same here. And then we go to the next one. We can see the same thing. Here's your Little Ice Age. And then with the post-Little Ice Age warming, hurricane frequency drops off. And this would have been the medieval warm period here, going back 800 years ago. Right? And then you see here, this particular compilation goes up during the Little Ice Age with the cold weather. And then with the warming weather, it's dropping down again. So this is not compatible with the notion that it's absolutely a given that the increase in warm temperatures is currently driving or going to drive the frequency and intensity of hurricanes. So anyways, I find that very interesting. So as far as hurricanes go, at least, you can't make the claim that hurricane intensity has shown any increasing trend at all, let's say since the mid 20th century. It's well within the bounds of what we would think normal. So then the question is that if there has been no increase in the number of hurricanes with the 1 degree warming since the end of the 19th century, and with 100 plus parts per million increase in carbon dioxide, if there should be this increase, should that not be a signal that we've already recognized? The point here is that you don't see the signal. You don't see a signal if 100 parts per million increase in carbon dioxide does not increase the numbers of hurricanes up to this point. Are we then justified in concluding that the next 100 parts per million is going to cause a drastic increase in hurricane intensity or frequency? And the answer is, I don't think we can extrapolate that from this data. Because this is data from different sources that is basically pointing to the same. Because what happens in cold weather, if the Arctic, say, for example, is more susceptible to the warming, it's going to be more susceptible in the reverse as well. In other words, we know that the Arctic has warmed up more than the lower latitudes in the last 100 years. If that is due to the 1.2 degree warming, roughly, if we reverse that, then presumably it will undo, right? Well, what that means then is that the higher latitudes in the Arctic realm becomes colder. Well, so it's also the latitudinal gradient, because if you think about this, the cold weather, like say we talked about this with regards to tornadoes. Tornadoes, you got cold Arctic fronts coming down, being swept across the Midwest. They're being shunted along the mountain barrier of the West, the Rocky Mountain front and so on, coming down, moving out onto the Great Plains area, where the cold air from the Arctic meets warm air coming up from the Gulf. And that particular topographical configuration of North America is what makes Midwest North America so conducive to tornadoes, and more tornadoes in the American Midwest than anywhere else on the planet. And it's that particular geography that does it. It's the meeting of hot and cold. So if you make the Arctic colder, but the lower latitudes stays relatively warm, that could increase hurricane frequency, and that might be what's going on here. I'm not an expert in this to where I can make any final conclusions, but that might very well be what is going on. But the takeaway here is that you can't conclude from this data we've looked at, that there is up to this point any trend in increasing power or frequency of hurricanes. So from that, are we confidently going to predict that the next 100 parts per million or the next 1 degree of warming is going to create that trend that has been missing so far? Well, I think that's a legitimate question. So then, the question becomes, the thing that you got to remember, the IPCC now was given the mandate to find the anthropogenic signal in climate change. And that's why, for example, they haven't really considered in depth the role of the sun. And when the IPCC was established, you got to remember, this was just at the very dawn of our deployment of solar satellites that we've been watching the sun now for.
No pun intended.
That's right. No pun intended. But we've been watching now for going on 30 years. We've accumulated a lot of data on the sun. Plus, we've also seen other suns in other parts of the galaxy that also seem to be going through a high degree of variability.
Oh, yeah.
Much higher than assumed for our own sun. And these are very sun-like stars that have been singled out. There's some point we have to dive into that, because that's extremely interesting stuff. But anyways, we do need to look at the sun. The sun is, I think, extremely important in all of this. Here's another interesting type of research, and this is past temperatures directly from Greenland ice sheet. This is an example of a study that came out in 1998, where they first realized that the layers of ice in the great ice sheets actually will take a signal of the ambient temperature at the time that ice was formed. So here's what they'll say. Measured temperatures down through an ice sheet relate directly to past surface temperature changes. Here, we use the measurements from 2 deep boreholes on the Greenland ice sheet to reconstruct past temperatures. The GRIP, that is the Greenland Ice Sheet Project, ice core, was successfully recovered in 1992. And the 3,028.6 meter deep liquid-filled borehole with a diameter of 13 centimeters was left undisturbed. So 3,028, that is 9,931 feet, or 1.88, almost 1.9 miles deep. So they have this core. They took out almost 2 miles of ice, 13 centimeters in diameter. Temperatures were then measured down through the borehole in 1993, 1994, and 1995. We used the measurements from 1995 because there was no remaining evidence of disturbances from the drilling, and the measurements were the most precise. The 2,037 meter deep ice core from Die 3 was recovered in 1981. We used temperature data from 1983 measurements. Histograms of the sampled geothermal heat flow density and of the temperature histories at each time before present can be made. Histograms from the GRIP reconstruction show that temperatures at the last glacial maximum were 23 plus or minus 2 degrees K colder than at present. That is a lot colder. That's K would be, same equivalent as Celsius. 23 plus or minus 2 degrees Celsius colder than present. So you could say 23, 23, 8. So that's going to be that's going to be almost 40 degrees Fahrenheit. The temperatures of this time, 25,000 years ago, reflect the cold temperatures seen on the measured temperature profile at a depth of 1,200 to 2,000 meters. The cold Younger Dryas and the warm Bolling Alarod periods are not resolved in the inverse construction. Because the temperature signals of these periods have been obliterated by thermal diffusion because of their short duration. But anyways, after the termination of the glacial period, temperatures in our record increased steadily, reaching a period 2.5 degrees K warmer than present during what is referred to as the climatic optimum at 8 to 5,000 years ago. So after the termination of the glacial period, they go from 23 degrees plus or minus colder than now up to 2.5 degrees K warmer than present during what is referred to as the climatic optimum, which lasted, they're giving the range of dates from 8,000 to 5,000 years ago. So that climatic optimum is what I've always kind of considered to be sort of maybe the source of these stories like the Garden of Eden and so on. We've talked about that, I think, somewhat. Be fun to circle back to that because that was a very pleasant time to be alive, actually. Following the CO temperatures cool to a minimum of 0.5 degrees K colder than the present at around 2,000 years. The record implies that the medieval period around 1000 AD was 1 degree warmer than present in Greenland. 2 cold periods, one at 1550 AD and at 1850 AD, are observed during the Little Ice Age, with temperatures 0.5 to 0.7 degrees below the present. After the Little Ice Age, temperatures reach a maximum around 1930 AD, but then temperatures have decreased during the last decades. The climate history for the most recent times is in agreement with direct measurements in the Arctic regions. The climate history for the last 500 years agrees with the general understanding of the climate in the Arctic region and can be used to verify the temperature amplitudes. The results show that the temperatures in general have decreased since the climatic optimum, and that no warming in Greenland is observed in the most recent decades. Now, of course, that was in 1998. How much warming has there been since then? Okay, what I'm going to do is I'm going to show...
Yeah, because I keep hearing and reading a Greenland ice sheet is receding, it's melting.
Well, it's melted on the margins and thickened during the zone of accumulation.
Okay.
Now, this is 98, and what they're doing is they're looking at ice layers, right? They're going down that borehole, and they're able to take information from the ice and determine the temperature when that ice was formed. Okay? So what the ice is showing is that there has been no warming. That's what the ice itself is showing.
Yeah.
Okay, so see here. Okay, so here is your contour plots of all grip temperature histograms as a function of time. So you've got, if you look at this, you see there's a red curved line in the center of this. It's the reconstructed temperature history. The white curves are the standard deviations of the reconstructions. And the blue curve, the blue line, which you see, is the present temperature. Okay. So A is the last, as it says, that's the last 100 years. So 100 years before present, here's your past temperatures, degrees centigrade at Greenland. It's getting colder and colder, and then it's showing here this warming coming up to here, and then it declines again right here in the last few decades.
Not seeing your cursor, but I can.
Here we go, right here.
There.
Sorry, right there. Then B is the last 10,000 years. So here you can very clearly see coming up out of the Ice Age, you can see the climatic optimum right here, the CO, climatic optimum. And then it dips down, then it comes back up, then it dips down again, and this would be the Little Ice Age right in here. And then this, the blue line, as it says, represents the present temperature. Okay, and then you've got C, which is the last 2,000 years, going back here, and you see, again, the last 2,000 years, here would be the medieval warm period, right here. See this is 1000 AD, so this was your great cathedral building era right here. Then it declines down, and again, the red line, as it says, is the reconstructed temperature history, and see how it actually dips below the blue line right here, the blue line being the present temperature. So this now, of course, is Greenland. You can't necessarily say this represents the whole planet. But the issue is, you know, you can look at one region, and if you're only looking at one region, you can say, okay, well, this one region is not representative of the whole planet, so it cannot be considered evidence. On the other hand, how many regions or local deviations do you have to have before you can assume, well, yeah, it probably is global? If, for example, we see an expansion of glaciers in the Alps, if we see an expansion of glaciers in Scandinavia, in North America, in the Andes, and in New Zealand, as we have now documented to have occurred during the Little Ice Age, we're getting pretty close to being able to safely assume that we're looking at a global event. Were there areas where it was maybe not? Well, I don't know. I have, maybe Africa, but I think the glaciers on Kilimanjaro expanded during the Little Ice Age. So again, you had to have a pretty broad aliquot of data that you're analyzing. But seems to me at this point that it sure is point in the direction that these are global signals and not just regional. So this is from this appeared in the journal Geology in April of 2000. Lead author Sarah L. Brown with the Department of Geology, University of Vermont, Burlington, Vermont, and John Southan, Center for Accelerator Mass Spectrometry at Lawrence Livermore National Laboratory, and a couple of others. The title of the article is A 10,000-Year Record of Extreme Hydrologic Events. Quantitative measures of extreme hydrologic events in the form of precipitation intensity and duration records exist for little more than 100 years of New England's history. Newspaper accounts and diaries extend this record back more than 300 years since European settlement began. Together, these records define the magnitude of extreme events and provide the design basis for local infrastructure. This paper demonstrates that ponds in mountainous New England, just as in similar landscapes around the world, have the potential to provide an even longer record that could reveal high-magnitude hydrologic events as far back as deglaciation more than 13,000 carbon-14 years ago. Lake sediments preserve a record of surface processes, and by inference, the geomorphic effects of past climates and hydrologic events. In particular, terrestrially derived inorganic layers in otherwise organic-rich lake sediment provide a record of basin-scale runoff and sedimentation events. In one northern Vermont water body, Ritterbush Pond, we find 52 such layers, many of which are considerably thicker than sediment layers deposited during the past 300 years, for which we know at least relative storm intensity. This record of extreme hydrologic events suggests that New England is unprepared for the magnitude and thus destructive potential of future storms. The 52 discrete inorganic layers represent an individual erosional event in the watershed that caused an episode of terrestrial sediment delivery to Ritterbush Pond. What caused the hydrologic and or geomorphic conditions that repeatedly allowed sediment transport to Ritterbush Pond? The most likely trigger for the deposition of coarser terrestrial sediment layers is runoff triggered by hydrologic events. Inorganic layer deposition in Ritterbush Pond is most likely the result of storms, including rain on snow events, which increase rates of hill slope erosion, stream channel scouring, and pond marginal sediment reworking. Specifically, we suggest that the terrestrial sediment stored in the watershed and at the pond margins is transported toward the center during storm events that significantly increase stream discharge and erosion. We can make rough estimates of storm magnitude represented by the layers deposited in Ritterbush Pond by using historic weather data, the modeled age of events, and the thickness of the inorganic deposits. Ritterbush Pond core C2 reveals only a single 1 centimeter thick layer within deposits of the last 300 years. The modeled age of the layer is consistent with the date of the largest storm in Vermont's written history, the flood of record 1927. Okay, so you had a 1 centimeter thick layer that dates right to Vermont's written record from written history, the flood of record 1927. If layer thickness is a proxy for storm magnitude, then 18 of the 52 events we identified in the Ritterbush Pond cores were larger than the 1927 flood. There was a layer that was 9 centimeters thick, 9.5, another one at 10 centimeter thick layers deposited at 2,600 years ago, 6,840 years ago, and 9,440 calibrated years before present. These three, you're talking basically 10 times the thickness of the largest recorded storm of the last 300 years. Okay, let that sink in. Those three are particularly striking and imply hydrologic events much larger than any witnessed during 300 years of Western settlement. So that's now the question would be, how many other studies would confirm that? This is one study from Vermont, and it's showing that there were storms that were apparently on the order of 10 times more, of 10 times greater magnitude and intensity of the greatest storm of record of the last 300 years. So that must have been one hell of a storm. So the question, though, is if you could find comparable environments to take samples in other places, what would you find?
Yeah,
is this something? Is this an outlier?
Right.
Or is this unique, or is this going to be typical of what you can find? And without getting into it, what I've seen suggests that it's typical, that there are enormous amounts of evidence that would suggest extreme hydrologic, what they're calling hydrologic events, which are going to be directly related to storms, which encompass everything.
Do you think that this is just because there's so much literature on this stuff? This is known by the people who are kind of pushing the climate change agenda because they know eventually a massive storm is going to come, and they're preparing. It's like the narrative is like storms are going to get worse.
Yeah,
so it's like it would play right into their
it's like
hands if one of these giant storms happens, then they're like, see?
Yeah, it's like they know that we're actually in a period where the storms are not very bad. Yeah. Historically, they've been much worse, so they can say the storms are going to get worse.
Yeah, they can easily say this, knowing that there's a pretty good probability that we will get some bad storms. Like, it will be worse.
Well, there is. And that was in one of the previous, quotes that I read was the concern about, and even in this one, the concern that, are we prepared for that magnitude of storms? And here's the thing, the irony of the whole situation is, to me, that the solutions being proposed for dealing with climate change would actually make us more vulnerable.
Right. The evidence seems to be that the colder periods makes worse storms, especially with the hurricanes, the core samples from the holes.
Mm-hmm, mm-hmm.
So if we reduce CO2 and if that actually makes it cooler, then we're going to have worse storms.
Or if there's something else besides CO2 altogether that's driving this.
Yeah. But the narrative is like we need to reduce CO2 so it doesn't warm.
Right.
So if they're right, which they're probably not, if you reduce CO2 and it gets cooler, then the evidence states that that's when we'll have the worst storm.
Well, that seems to be consistent with the
evidence.
And we've looked at a pretty fair amount of evidence over the last half dozen or 10 episodes or so to kind of point in that direction, that there have been times, in recent geological history of the planet, the last millennia, couple of millenniums, when, the intensity of these events have been greater than we've seen in the last 100 or 200. And this is a perfect example of that. Now, I would like to scour the literature and find if there have been parallel studies done in other ponds that exist, or lakes. Lake, I would imagine, would be the similar, that would show, these thick layers. But I mean, when you think about that, that's pretty significant that the greatest storm of record of the last 300 years was a storm in 1927. And there is deposits of 3 events that look like they were an order of magnitude more extreme. Be interesting to research that 1927 event and see what accounts there were and what wind speeds there were, how much rainfall there was, to get an idea. I think I will do that. So,
was it Ian that went up the coastline and went all the way up
last summer? You mean?
I think, well, it was before that, because we went up there. We have relatives up there, and we went up and we saw some of the destruction. Hit New York, and
Sandy?
Maybe it was Sandy.
Hurricane, Storm Sandy, whatever. Yeah. Hurricane, tropical storm, whatever they call it, Sandy.
Yeah. Yep. It caused an enormous amount of erosion in some places in the mountain streams, undercut entire houses that basically fell or were in the process of falling. Saw some of that. It did a lot of damage. Mm-hmm. So if that's nothing compared to the storms that they've had deep in the past, then I do think it's interesting that these people are saying, well, we're not prepared. The guy who's looking at the hurricane data saying the Caribbean islands are not prepared for the level of storms that we see in the data that's caught in the coarse grains in these holes. Yeah.
And storms that were occurring during times of cooler temperature.
Right. Cooler temperatures. Yeah.
Well, frankly, if you look back over the recent history of the last 10 or 20 years, nobody's ever prepared for hurricanes of any magnitude in this country. I mean, it just seems like everybody's always surprised when a storm hits. It's like, holy shit, that was the biggest storm we've ever seen, you know?
Well, we certainly saw that down there south of Tampa when I went down there to do the interview with Tucker. I mean, we went right through the dead center of where, which hurricane was that made landfall? And the destruction was pretty extraordinary.
Yeah, I've forgotten the name of that one, but the one that came from the Gulf and across going east. But yeah, my point is that we're going to have hurricanes. You know, they're going to be of varying magnitudes, and nobody really seems to be able to predict them. But it always just seems that everybody's always surprised when a hurricane hits. It always takes a different turn. It jogs left, jogs right, whatever.
Yep. Hard to predict them.
Right, and consequently, everybody's always surprised, and the media is always surprised. It's like, come on, you live in Florida, you live along the Gulf Coast, you've been building on the beaches for years, and what do you expect?
Well, yeah, that's the point, and that's why you can't use the dollar value of damage to infrastructure as a direct correlation of intensity or frequency of hurricanes.
Yeah.
But yeah, one of the things that really intrigued me, and this was, going back to pictures that I've seen of, the bombings of Hiroshima and Nagasaki and, great destructions, hurricanes and stuff. I saw this myself down there in near Boca Grande, where the hurricane made landfall. Was you would see houses demolished, but then there's one house standing there in the middle. And I'm going, okay, what? Is that just a vagary of the wind, the atmosphere, or what's different about that house that the one on both sides of it got blown down and it's still standing there? Or the roofs got blown off of houses. I saw a lot of that. But, I know myself now when we build like that and we build a roof, we do metal straps, hurricane straps, to tie the rafters to the wall top plates. And
then it picks up the whole house instead of just the roof.
Well, then what you do is you bolt the bottom plates, you bolt the frame into
to the foundation,
to the foundation. So it's got to lift the whole foundation. And then if you've got 2 foot wide by 1 foot thick footers, you're pretty good. I mean, it may blow windows out, but it's not going to, I don't know, maybe a 500 or 1,000 mile an hour wind is going to demolish anything. But a typical, even a full strength hurricane won't lift the whole house up like on Wizard of Oz or something.
Right,
and
just the whole house.
The whole house is up there twirling in the vortex with cows and things flying by. No, Russ, I don't think that would happen. Oh. But yeah, I mean, the point is that, actually, you ask yourself, I mean, so there was a lot of solar collectors on roofs down there that didn't fare too well. That was another thing. Yeah. So the question is, if we stop using fossil fuels because we believe that fossil fuels are causing a climate catastrophe, that means there's a whole lot of implications as far as, our ability, our scientific and technological ability to respond to events. If we don't have, access to quantity of energy.
Yeah,
portable.
Yeah, mobile, portable energy sources.
Yeah.
And that, you were talking about the dollar value. I mean, the dollar value of a square foot of roofing that has solar panels on it is incredibly higher than just shingles.
Yeah.
So then you destroy one roof and it's just a massive bill.
Yes.
So.
Yeah.
Yep, that's a good point.
Yeah, it was amazing to see that firsthand. And the amount of trees uprooted, thousands of trees just uprooted. And I'm thinking, what would that have been like? I mean, if all around you trees are being large, 60, 70 foot tall trees are being uprooted.
Yeah.
That would be kind of a scary thing.
Yes.
But yeah, I mean, they were already underway. You could see they were underway, cleaning stuff up. But you go down the main highway there, and there would be piles of debris just lining for miles on both sides of the highway. Because they're pulling it together, and then, even in the week or so that I was down there, and then went back again. Didn't I go back again? Yeah, they had already removed a lot of the stuff. So I mean, they were busy cleaning up. But it sure did tell me that, yeah, if I'm guessing, and I'm sure there's going to be engineering studies that come out, which I'm going to be very interested in reading about, what measures were effective in preventing houses from getting demolished and what measures were not taken that caused other houses to become demolished.
Nuke 'em. Who's in favor of nuking hurricanes for science? I think we should try it.
So once it gets started, blow a nuke up in the middle of it and see what happens.
I just want to know.
Let's see what happens. So all of it spawns 100 smaller hurricanes.
Yes.
And each then grows into this monster.
Well,
shedding radioactive.
Yes, and they're radioactive.
Yeah. Radioactive hurricane.
It'd be awesome.
Oh, yeah, that would be awesome,
science.
wouldn't it, Kyle?
We need to see what it's going to do.
But I thought that study from that Ritterbusch pond, I thought that was quite interesting.
That is cool.
That's great.
No, it's a great episode.
It's a good
A
episode.
lot of really good info.
Thanks everybody for joining us and watching. Remember, RandallCarlson.com for all your Randall Carlson needs. Sign up for the newsletter. Randall writes something for it it's once a month, right? Is it once a month?
I just went out. Some of the stuff that I talked about in there was quite interesting, I think. I talked about, I did talk about some climate change studies in China and Tibet. We could get into that maybe next episode. And I also talked about new insights into the Hopewell phenomenon. And this is quite interesting. That the duration of the whole, very similar here, the idea, and I'll just make this very quick. In the older concepts, the entirety of the Hopewellian enterprise that created all of that monumental earthwork structures and so forth was 700 years. Okay. Well, these new studies have reduced that to 250 years. So it's going to be interesting to ponder the implications of that, because now you're looking at less than, or about a third of the time, allowable time to create that incredible, amazing stuff there. And then what else? Yeah, I mean, I talked about it's very interesting stuff to do with climate change, and a couple of new studies. So, anyways, interesting stuff. And then one of the studies was extreme synoptic and climate events in ancient Mesopotamia, the development of cultures and civilizations in China, classical Maya, how all of these may have been affected by natural climate change. And this was the study I talked about specifically in this newsletter that just went out, was focusing primarily on Central Asia, because that's where a lot of research had not been done compared to other places. And again, it shows the same pattern. Anyhow, and they went into their conclusion is that one of the two primary drivers are changes in ocean circulation and changes in the sun. So we'll be picking up on, discussions about the sun.
All right. And we got a Montana trip coming up. So sign up for that. Contact@thecabin.com or randallcarlson.com. You can find it at the tours area.
All right. Finally, last thing I'll say is randallcarlson.com is the only legitimate source.
Yep.
Sacred Geometry International is still fraudulently selling my stuff, trying to as we get more and more attention and increase the numbers, he's trying to ride on our coattails and is using optimization techniques to, when people go to look for me, they're being directed to Sacred Geometry International, where he's then trying to monetize my work. So if people were so inclined, I would like the more people that know that scam is going on, the better. So talk about it, inform people that it's fraudulent, and you couldn't even imagine how appreciative I would be if that finally came to an end.
Yes.
Thanks, guys.
All right. Thank you. Great show.
Thank you.
Good night.
Good night, everybody.
All right. Good night.
Nuke 'em.